I have the pleasure of introducing Alexandre d'Astus. Alexandre is currently a PhD student at the Polytechnique Montreal and is exploring new ways to perform B0 shimming to achieve better results in MRI. Alexandre has keen interest in supporting reproducible and open science like us all. And most notably, he is a main developer of the open source tool, the Shimming Toolbox, which aims to provide the necessary platform and tools to develop and perform B0 and B1 shimming experiments. Personally, this is a topic I'm actively looking to start exploring for a problem we're seeing at our lab. So I'm really, really pumped to hear and see what he's developed in this talk today. Alexandre, I will gladly pass it over to you.
All right, thank you. So hello, everyone, and thank you for the kind introduction and to the organizers. And today I'll be doing a quick demo of Shimming Toolbox. And as Joseph mentioned, this is a software tool to perform B0 shimming as well as B1 shimming. And today I will mainly discuss about B0. I will be starting with a PowerPoint describing the general capabilities, and then I will switch to a live demo. So hopefully everything works well for that. All right, so let's start. So what is shimming? So shimming, the goal is to make the field as close to the desired field as possible. So on the left, there's a field map describing what the field offset is. And then on the right is hopefully what you get after shimming, which is a much better image as close to, for example, 3 Tesla, if your scanner is a 3 Tesla. So why do we do that? Well, B0 shimming is important because you get good image quality. If you don't have good shimming, then you're just going to get poor image quality. It can reduce loss of signal from T2 star dephasing. It reduces geometry distortions. It can reduce ghosting, blurring, and ringing artifacts, and it can improve the spectral line width in MRS. It can also do many other things, but in general, that's the main points. So what is Shimming Toolbox? Well, it's a software package to perform active B0 shimming, and then it can also do B1 shimming. Shimming Toolbox supports many ways to shim, but the most used one is based on field maps. Using this method, there are many ways to customize shimming, such as using a whole volume, similarly to what the scanner does. You can also do slice-wise shimming, or even real-time shimming. And slice-wise shimming is going to change the shim parameters for each slice. It's also possible to use spherical harmonics, as well as custom design coils. So let's get started with an overview of Shimming Toolbox. So it's a software program that combines multiple tools to perform B0 shimming. It can be installed on a computer that can be brought to the scanner room and compute shimming coefficients with a graphical user interface, or from the command line using scripts to more easily reproduce experiments. You can acquire a B0 field map of the target region, possibly acquire an acquisition less susceptible to B0 inhomogeneities to compute a mask, if necessary, and a target acquisition, which we're going to shim, that's to know the geometry of the acquisition. So Shimming Toolbox includes tools to convert the DICOM files to standardized BIDS datasets by leveraging DICOM to NIIX and DICOM to BIDS. And it can create masks using BET and SCT or your favorite segmentation software, and then can compute the B0 shimming coefficients. These tools allow to perform static, so volume-wise, or dynamic, or slice-wise, and real-time shimming using field map-based methods, as well as other methods, as I've mentioned. Custom coils, as well as scanner, gradient, and shim coils can be used to compute the shim coefficients, allowing to shim using the scanner hardware as well as custom hardware. And then those coefficients are sent back to the MRI console if you're using this for harmonics, or you can use your own shim amplifiers. So that was it for my quick introduction. So I'll jump into the demo right away. So first of all, if you want to download Shimming Toolbox, what can you do? How do you do that? So let's open up a browser. So the first thing you would want to do is just write Shimming Toolbox or go to our website, which I'll have linked at the end. but you can just go to Shimming Toolbox on your browser. And then the first link is our site with documentation, and then at the bottom is our GitHub repo with everything in there with tests and everything you would need to look at the source code. So if we go into on the website, you can see a brief description. You have installation instructions, some tutorials, the command line tools that could be used, and then some section on developers if you want to contribute. So if you want to install it, we had a question earlier, but it's available on both macOS, Linux, and Windows. The only difference being that Mac and Linux have a GUI and Windows only supports the command line. So to install, it's pretty simple. You git clone and then make install and then source your bash.rc, and then that's it. So I've already done that. And then you would pick up right here. So I can go on the command line and simply type Shimming Toolbox, and this is going to launch Fossilize, which is used as a viewer. And then what we've done is we've added a plugin into Fossilize, as you can see here. So that's the main interface for Shimming Toolbox. You can see B1, B0, and then a couple more options that you can do. So by changing these, you can input, do different functions. And then on the right, you can see oh, sorry about that. You're not seeing my screen. Let me start over. All right. So yeah, so you can see that it launched Fossilize, and then you can see the tab, the plugin for Shimming Toolbox. And the B0 that we're going to be using is here. And you can see on the right, that would be essentially terminal outputs. So we're going to be looking at that later. All right, so the first thing we're going to be doing is, we're going to be doing two things. We're going to be doing two experiments. The first one we're going to be doing is a volume shim using the spherical harmonics of the scanner. So something that the scanner can already do, but let's just see what it entails to do the most basic kind of shimming, just to see how to do that. So let's jump to what we need to do that. So to do a volume shim, first thing we're going to need is a field map to know the field. We're going to need a mask, which we're going to be computing based on an anatomical image. And then we will need a target image, which is going to be an EPI image, or a set of EPI images that we're going to try to improve. We also need core profiles. So in our case, we're going to be using spherical harmonics. And the idea is to know where the field is, and then shim on that, and then output a text file. All right. So here I have some data. I have an MP range acquisition, so our anatomical image. I have field mapping data, and then I have our EPI acquisition. So what we're going to do is jump to DICOM to Nifty, because our Shimming Toolbox basically uses DICOMs. Sorry about that, uses Nifties. So we're going to be converting to Nifty. So what we can do is click on the input folder, select our data, which is going to be our DICOMs, and then we're going to open that, and that inputs the path in there. We're going to be just calling this a demo, and then everything else is already good to go. The output is going to be right here. So you can see right here that we are, the command that we've just ran is output here. And what we could do is put it on the command line, and that would essentially run the exact same thing. So that's really convenient if you want to automate your things, your workflow, or if you want to write a script. But for now, let's jump back to the plugin. So you can see a bunch of output. So that would be the output on your terminal. So on the left, bottom left, you can see a bunch of acquisitions. Let me make that bigger. So it automatically loaded the data. So you can see our EPI acquisition, field map acquisition, as well as our MP range acquisition. All right, so let's bring that back. So the first thing we're going to be doing is computing a mask. So we're going to be trying to segment the brain. So we have bet that we can be used from the GUI. Bet that comes from I believe fossilized, not fossilized, sorry, FSL. So what you can do is you can in the input you would want to put your path. So what we've done is we've integrated it with fossilize, and if you select in the overlay and click on the button, it puts the path in there, so that goes pretty fast. Then the output is going to be just bet, and if you're ever unsure about what do you need, you can just hover over the little eye, and that's going to tell you the information. So you click run, and it's going to run, and you can see we have our mask. We can fix that a little bit. I know some parameters that I've tried before that worked a little bit better. So we can just rerun it, and it's going to overwrite the previous file. It's going to load it in, and you can see a little bit better. Let's remove this one. The next thing we can do is we can, for example, erode or dilate a mask. So for now, we're going to be eroding it. So we can select our mask. We can erode. We're going to be using a kernel size of 3, so that's just going to remove 1 voxel. And then we can run, and it's going to be, you can see here, it just eroded it. Pretty simple. All right, so let's, now that we have a mask, we can compute a field map. So what we can do is go to this field mapping tab. What we have is a 2 echo acquisition, but the scanner already computed a phase difference for us. So for that, we can just simply use 1. Click on the phase difference. Let's remove the mask a little bit. So click on the phase difference, and then that's going to load it in. You can select the magnitude, load it in. And then the unwrapping region, we're going to be using the mask we've just created, which is right here. And then as an unwrapper, we can use Prelude because we have it with FSL, and then we can run this. So the output, again, here's our field map calculated, and this is in Hertz. So now that we have our field map, we have pretty much everything we need to perform B0 shimming. So here's the main tab with all the options. So if we wanted to do some other algorithms, we would go here. But if we do volume or dynamic shimming, that's where we need to go. So as I mentioned before, we're going to be trying to do a volume shim using the spherical harmonics of the scanner. So we don't have a custom coil, so we can just put 0 or leave as blank. We can select our field map and load it in. The input ANAT is our target and target image, which is our EPI image. So let's select it. Our mask, we're going to be using our eroded mask, a little bit smaller than the field map. And then we're going to, we have different optimizers that we can use. For now, let's just use, for example, the pseudo inverse. And then our slice ordering, we're just going to be doing a volume shim for now. And then the scanner order, this is 70 data with a third, and the scanner has a third order, so we can select it. And then the output format, that's for our text file. So we're going to be doing chronological per coil. That's going to be a little bit easier. And then everything else is good to go, I believe. So pseudo inverse doesn't respect constraints, which is why I haven't put anything as a scanner constraint. But if we wanted to, we could put least squares, which is gonna restrict constraint, which we're gonna be trying later. All right, so a a bunch of output here, but you can also see that we've loaded a field map with our calculated shim, what we expect the shim to be. So what we can first do is look at our, first let's remove everything else, and then let's take our field map and rescale it to -100 to 100 hertz. So this is our original field map that we've acquired. And then if we do the same thing for our computed field map, you can see that it's a little bit better. So if I wanted to go into more detail, you can see the output that we've done earlier. So here's output dynamic shim, and you can see here the figure showing shim versus unshim. So it opened on my other screen, but you can see on the left, let me make that a little bit bigger. So you can see on the left the before shimming, and then on the right after shimming, which is a little bit improved. So 61 hertz of standard deviation, and then an average of 0. All right, so what if you wanted to apply it on the scanner? Well, you have your data here, your text files. So if I open it up, let's open the other one. So here it is. I don't know if that's, let me make that a bit bigger. So you can see your coefficients. You can see it's in the order that you've put. So this is your frequency, so -12 hertz, your X, Y, as well as Z, and then your second order, and then your third order coefficients. And what we've done is currently Shimming Toolbox supports Siemens, Philips, as well as GE. And we've put these coefficients as if you were to enter them in the scanner. So they've been reordered as well as rescaled so that they are as you'd expect when you enter them in the scanner. All right, so that's for a volume shim. Let me go to my second example, which is a slice-wise shim. So slice-wise shimming, really similar to volume shim. The difference is that you take a much smaller region and then you optimize for different for each of those regions for each slice. That's only relevant for 2D acquisitions, obviously, but that's something that you can do. So they take the same input. The only difference is we're going to be looking at the target image, and we're going to be taking that mask and making a much smaller region to shim, and then shim, I think 50 times because there are 50 slices. The other difference we're going to be doing is we're going to be using a custom coil. So instead of the spherical harmonics of the scanner. So in the data, I have something called custom coils, and I can load that in as well. So those are the coil profiles. So I'll also rescale them so that we can see them better. But the coil profiles are essentially in hertz per amp. So they tell how much each channel of the custom coil changes the field per amount of current. So each volume is going to have a different geometry because the loop of the channel is at a different spatial location. The other thing that I have in here is a config file, which is going to mention the constraints of our coil. So let me again make this bigger. But you can see that our coil is going to be restricted from -2.5 amp to 2.5 amp, and then the maximum coefficient, or the sum of the coefficients, is going to be restricted to 20. All right, so if you wanted to do that to enter that in the interface, well, now we have one custom coil, so that pops another field, which is going to be for inputting a coil. So we're going to be importing our profiles. Another way that you can do instead of clicking on the button is just to drag it in. And so we can do this, and then that's going to drag it in, and then you can do the same thing for the config file. Our field map stays the same. Target image stays the same. Mask stays the same. And then if we want to respect the constraints, as I mentioned earlier, I can select these squares. And then we're going to be using different optimizer criteria. For example, we can use the RMSE. We could also select a regularization factor. So if we wanted to favor solutions with low recurrence, we could use that. For now, I won't be using it. The slice ordering is going to be auto detect. So this is going to be a slice-wise shimming. You could decide to output using an ascending or descending or interleave acquisition, but auto detect for Siemens works pretty well. We're not going to be using the spherical harmonics of the scanner. And then the custom coil output format is going to be chronological per coil as well. And then this, I can run this. So this is going to take a little bit over 30 seconds. The reason is it's 32 channel coil, and then it's doing 50 optimizations. So in the meantime, what I can show you is some results that we've actually acquired with a really similar parameter set. So here is the slide. So on the left, you can see the field map we've been playing with. And then this was acquired with a second order shim of the scanner. And then on the right, you can see what Shimming Toolbox has predicted and what was actually acquired with the AC/DC using a slice-wise acquisition. On the right, you can see the MPRH reference, which we've been also using. And then what we've done is we've acquired our EPI images with reversed phase encoding directions. So that's going to change the distortion orientation. And you can see that there's distortions where you'd expect in the global second order shim. And then there's much less where you also expect that in the when using the dynamic, so slice-wise coil, slice-wise custom coil. All right. So here, this should be on the verge of finishing up. There you go. So you can see right here that this is our shimmed image. If I also rescale it to a -100 to 100, this is our original field map. There we go. You can see that it's better. And if we go to our, oh, I know what happened. Right, let's go to the, right here. So for your information, I didn't change the name of the output folder. So it went in the same folder. So that's why there's two in there. But if I go and look at this figure for shimmed versus unshimmed, so the same thing as we saw earlier, but this time using slice-wise shimming with the AC/DC coil. So this is before shimming. And then after, we can see a 44 hertz, so much better improvement. We can also look at the custom coil without our FATSA. All right. So you can see a lot more coefficients, obviously, because there's 32 channels. But you can also see that there's one set of coefficient for each slice. And then you can also see that they've been constrained to minus 2.5 to 2.5 amps. And again, you could change the regularization factor if you wanted to have lower currents on your coil, as well as your config file. All right, so that concludes my live portion of the demo. So I'll go back to just a simple conclusion slide. So Shimming Toolbox is an open source software for B0 and B1 shimming. It's available on the command line as well as in a GUI, as you saw, on Windows, on on Linux as well as Mac OS. The idea is to foster collaboration and make advanced shimming accessible and reproducible for as many people as possible. And you can see a link to our website if you're interested in trying it out. And then if you have any question, I'm happy to answer. And if you have questions later, you can also go to our Shimming Toolbox website and open an issue or start a discussion there. So thank you.